Hello, Chem 30. This is our 6th lesson in the acid-base unit. This is titration analysis, neutralization, and excess reactants. In this lesson, we are going to recall acid-base titrations from Chemistry 20, and we will go through 2 examples. Recalling titrations. To perform a titration calculation, we must first start with a balanced chemical equation. Then we can move on to find the average volume of the titrant added. Remember, to find an average volume, we must use at least 3 trials that fall within a 0.2 milliliter range. Any other trials that do not fall within the 0.2 milliliter range, we will disregard. We can then start our calculation with the substance which both the volume and concentration are provided. Remember that titration reactions go to completion. They are quantitative reactions. Example number 1. Use the following data to calculate the unknown concentration of sodium hydroxide if it was titrated into 10 milliliters of 0.111 moles per liter sulfuric acid. Pause the video and attempt this example. The title of our titration table is very important. It says titration of 10 milliliters of 0.111 moles per liter sulfuric acid. This tells me that the set volume is 10 milliliters for sulfuric acid, which is in the Erlenmeyer flask. Therefore, the volumes in the table correspond to the volume of sodium hydroxide. We have to find the volume added in each trial by taking the final reading minus the initial reading. These are the volumes added of sodium hydroxide in each trial. Notice how trial 1 and 3 are not used. That is because their value does not fall within the 0.2 milliliter range. To find the average volume of sodium hydroxide, we are going to take the average of 2, 4, and 5, seen here. That will give us an average volume of sodium hydroxide of 11.26 milliliters. Remember, do not round this value yet. Before we move forward, let's take a look at the significant digits going into the calculation. From the initial question, we have 4 significant digits and 3 significant digits. We also have to consider the significant digits used from the table. Since we only used trials 2, 4, and 5, each of these values has 3 significant digits. Therefore, our end answer should have 3 significant digits. Note, if we did use trial 1, our end answer would have 2 significant digits, and that is from the 0.30 value. But since we only used trials 2, 4, and 5, our end answer, again, will have 3 significant digits. We can start our titration calculation with a balanced chemical equation. Notice the volume and concentration of sulfuric acid and the volume of sodium hydroxide. We can now move forward with the calculation to solve for the concentration of sodium hydroxide. To do so, we are going to start with the volume of sulfuric acid in liters, and we are going to times it by the moles per liter. This will get our answer into moles of sulfuric acid. We can then use the molar ratio in the chemical equation to convert our answer to moles of sodium hydroxide. Once we have the moles of sodium hydroxide, we can then divide it by the volume in liters of sodium hydroxide. This will get our answer into concentration. Our end answer for the concentration of sodium hydroxide is 0.197 moles per liter, 3 significant digits. Consider the following. When more acid or base is added to neutralize another solution that is needed, the equivalence point is overshot. This means that you will have an excess of one solution. Example number 2. What is the pH of the final solution when 21 milliliters of 0.10 moles per liter solution of sodium hydroxide is added to 20 milliliters of 0.10 moles per liter hydrochloric acid? Pause the video and attempt this example. First up, we have to calculate the limiting and access reactants using the have-have, need-need method. We then need to determine the amount of access reactant left over. That access reactant will either ionize or dissociate to produce H3O+ or OH-. We have to find the concentration of one of these products depending on which is formed. Once we have the concentration, we can then calculate the pH of the final solution. We're going to start this calculation with a balanced chemical equation. We are then going to find the moles that we have of each reactant. To do so, we are going to take the volume in liters times by the moles per liter. That will give us 0.0021 moles of sodium hydroxide. We are going to perform the same calculation to find the moles that we have of hydrochloric acid. We are then going to find the moles that we need of hydrochloric acid if we were to react all of the sodium hydroxide. We are also going to do the same calculation to find the moles that we need of sodium hydroxide if we were to react all of the hydrochloric acid. We now have to compare the have and need values. First up, we can see that we have this amount of hydrochloric acid, but in order for the reaction, we need this amount. We can tell that we need more hydrochloric acid than we have. Therefore, it will be the limiting reactant. Vice versa, we have 0.0021 moles of sodium hydroxide. And if we were to react all of the hydrochloric acid, this is what we would need of sodium hydroxide, 0.0020 moles. We have more than we need, therefore sodium hydroxide is our access reactant. We now need to find how much we have left over in moles of sodium hydroxide. So we will take what we have minus what we needed in the reaction to give us a remaining 0.0001 moles of sodium hydroxide left over in the solution. Sodium hydroxide is a strong base and dissociates in water. It dissociates to produce a 1:1:1 ratio. We can then take the moles of sodium hydroxide and convert it to moles of hydroxide using stoichiometry and the molar ratio in the chemical equation. We can then take the moles of hydroxide and divide it by the total volume of the solution. That is 20 milliliters plus 21 milliliters. That gives us a concentration of hydroxide of 2.43 times 10 to the minus 3 moles per liter. We can then find the pOH, which is equal to the negative log of the concentration of hydroxide. That gives us a value of 2.6143 ... We can then find the pH by taking 14 minus the pOH. That gives us a pH of 11.39. That is 2 significant digits and our final answer, because we started with 2 significant digits going in to the calculation. Moving forward, we will look at pH curves and indicators.